In this lecture, I will discuss the mechanical properties of waves, and we will focus predominantly on transverse waves and discuss resonance, standing waves, interference, and so on. Waves can be discussed in several different contexts. So we have mechanical waves, and those waves are governed by Newton's laws. They can exist only within a material medium, such as solids, gases, or liquids. And examples of such waves are water waves, sound waves, seismic waves, waves in a string, for example, in a guitar string, and so on. Then we have electromagnetic waves. These waves do not require a medium for propagation. The most common example of such a wave is visible light, but we also have UV, infrared, radio, TV, gamma, X-rays, and so on and so forth. Those waves propagate with the same speed in vacuum, and that is the speed of light. And then we have matter waves, which are waves associated with electrons, protons, or other fundamental particles moving inside, let's say, a bulk material. We are not going to discuss those types of waves in this course. They are subject of study by solid-state physics. By the nature of propagation of the waves and oscillation of the particles of the medium, we have two main types of waves. We have transverse waves, and then we have longitudinal waves. First, let's discuss transverse waves. In the cartoon here, we have a person holding onto a rope that is tied at one end. And so the person produces a uniform periodic disturbance in the rope by shaking their hand up and down. And so with every up and down motion of the hand, a pulse is generated in the rope. And so this pulse will travel down the rope away from the hand of the person. And so when multiple pulses are created one after the other, then the rope starts to look as if a sinusoid curve. And so that looks like a wave. And so a periodic wave is created this way, and this wave propagates down the rope. Now, the important part here is to understand that the particles of the rope themselves do not move down the rope. Because if that was the case, then at some point there will be no more rope for the person to hold onto. What happens is the particles of the rope oscillate vertically up and down as the wave passes through that portion of the rope. And so the wave propagates horizontally down the rope, but the particles of the rope oscillate perpendicularly to the direction of propagation. And so because of that, waves that propagate in such manner are called transverse waves. I will dedicate a separate slide at the end of the presentation, explaining a little bit more in detail how the oscillations of the particles in the rope look like with respect to the way the wave propagates down the rope. Now let's talk about longitudinal waves. So longitudinal waves are sound waves. Only sound waves can be longitudinal. Sound waves can propagate in solids, liquids, and gases. And so the example here is for sound waves generated in gas, in air more specifically. So what we have here is a pipe that is closed on one end. That end is a piston that can freely move back and forth. And so a person generates disturbances in the gas by moving the piston back and forth in a uniform manner. So the piston moves in each direction by the same amount, and then the frequency with which the person moves the piston is doesn't change, it's the same. And so what happens is the piston will mechanically collide with the molecules closest to it and will push them to the right. So then those molecules will collide with molecules next to them, and they will collide with molecules next to them, and so on and so forth. And effectively, a compression of the air molecules is created close to the piston. Okay, so that compression of molecules will move to the right. But behind the compression, there's plenty of molecules left, and those molecules are just not as concentrated. And so when the piston pushes on those, it's going to create another compression, which will be moving to the right as well. Of course, there is more molecules behind that new compression, so when the piston pushes on them, another compression is created. And so now we have a set of 3 compressions propagating to the right. Of course, air molecules do not just move in the same direction all the time. We have diffusion happening, and so molecules will move around however they want. So there will be always new supply of molecules in front of the piston to create a new compression. But we are also going to end up with regions where there is less dense population of molecules between the compressions. And so we now have a system of compressions and rarefactions where the molecules are less dense. And so this is a periodic occurrence due to the fact that the piston is being moved in a periodic fashion with the same frequency and with the same amplitude. And so a sound wave is created in this pipe by this process. And so now you notice that the sound wave travels to the right in this particular example, and the compressions and rarefactions obviously travel to the right. But the molecules of the gas also oscillate in the same direction as the direction of propagation of the sound wave. And that's why we call those types of waves longitudinal waves. So one more time, only sound waves are longitudinal waves. All other waves are transverse. So mechanical waves in a rope, mechanical waves on a string, electromagnetic waves, they're all transverse waves. Next, let's look at the shape of a wave that is generated along a rope as shown in this graph here, a series of graphs on the right. So here is my wave that is propagating down the rope in positive x direction. We can identify several different specific components of the wave. For example, we have maximum displacement from the x-axis, which we call the amplitude of the wave. We can measure the period of the wave, which would be the time for one complete cycle of the wave to pass through a certain point in space. So how do we identify a complete cycle? Well, a complete cycle will be, for example, this section of the wave. So the wave starts at x0, goes towards maximum, then towards minimum, then goes back to 0. And after that, the shape of the waveform starts to repeat itself. So one cycle is a unique portion of the wave after which the wave shape starts to repeat itself, or the waveform starts to repeat itself. So that is the time that it takes for one period to complete. So then I can also associate a length of the wave, or the wavelength, lambda, with the shape of the waveform. So one complete wavelength will be a section of the wave that is unique, after which the waveform shape starts to repeat itself. So for example here, the wavelength is this distance along the wave. So we start again from 0, go through maximum, then through minimum, reach 0 again, and then after that the shape of the wave starts to repeat itself. So the distance along the wave from here to here is the wavelength. And I can measure the wavelength from any point along the waveform as long as I follow the definition, the requirement for uniqueness of the shape. So for example, I can start from this maximum here, go through the minimum, go back to the next maximum, and so this distance along the wave is the wavelength. Or as indicated in the graph here, if I start from this position, go along the waveform, get back to that same position further down the waveform, that distance is the wavelength. So if you compare the definitions of a wavelength and the period of the wave, you will see that it takes exactly one period for one wavelength to pass through a certain point in the medium through which the wave is propagating. So looking at the waveform presented in these plots, one would see that these are plots of a sine function. And so because of that, the equation for a wave is given by this function right here. So now notice that the waveform depends both on position and time. So y is a function of x and t is equal to ym sine of k times x minus omega t. So ym is the amplitude of the wave, and then sine of kx minus omega t is the oscillating term, where kx minus omega t is the phase of the wave. K is known as the angular wave number. X gives us the position along the waveform. Omega is the angular frequency, and t is time. The phase here changes linearly with time, and due to the nature of the sine function, we know that this is a periodic process, and because of that, the sign itself will be changing between +1 and -1, and so that would depend on t. When this sign is equal to +1, then we have maximum positive displacement from the x-axis. When the sign is equal to -1, then we have maximum negative displacement from the x-axis. The wave number k is defined as 2 pi divided by the wavelength of the wave. K is termed the angular wave number. What is the meaning of K? Well, K essentially is the number of wavelengths that fit a unit length along the wavelength, or along the length of the material in which the wave propagates. The relationship between the wave number k and the wavelength lambda comes from the fact that the wave repeats after a period of 2 pi since this is a sine function and it's a 2 pi periodic. We know already what the angular frequency is. The angular frequency is simply related to the period as 2 pi divided by the period of the wave. And we also know the frequency of the wave f is related to the period as 1 divided by the period, or to the angular frequency as omega divided by 2 pi. So the new term here associated with waves is the angular wave number. And so one more time, this is the number of wavelengths that fit the number of wavelengths per unit length. Let's find out what's the expression for the wave speed, the speed with which the wave propagates down the medium, so let's say a rope, down the rope. So here we have one wave that propagates down the rope, and so initially the wave, colored in green, has this waveform, and that is the position of the wave along the rope. After some time delta t, the wave form has shifted by distance delta x. So if I take the ratio of delta x to delta t, or if I go into its limit version, that will be dx dt, I can find an expression for the speed with which the wave propagates down the medium, so the wave speed. So since this problem is about the propagation of the same wave down the rope, that means that the phase of this wave remains constant. So kx minus omega t is equal to a constant. Okay, so as the wave propagates in positive x direction, obviously the time component of the phase increases, but so does the spatial component of the wave, of the phase, and as a whole this remains constant, so that's not a problem. Alright, so now I will take the time derivative of the phase and let's see what it looks like. So we have k dx dt minus omega is equal to 0. So just as a reminder, the derivative of a constant is equal to 0. So now dx dt is defined as the velocity. And so then combining the two, let's write it on the other side of the graph, I get that kv minus omega is equal to 0, or v is equal to omega divided by k. And this is the result that's shown here in the green box. So the wave speed v is equal to the angular frequency divided by the angular wave number. Now, if you remember, omega is related to the period of the wave, and k is related to the wavelength of the wave. So if I combine the two, I can also rewrite the wave speed as lambda divided by the period, as it's shown right here. And finally, remembering that the frequency of the wave is related to the period, I can rewrite the wave speed as v is equal to lambda f. So the wave speed is equal to the wavelength times the frequency of the wave. This is an extremely important relationship because it applies for any kind of wave, transverse or longitudinal, wave that propagates in medium or an electromagnetic wave. It doesn't matter. For all waves, this is an important relationship. So one more time, the speed of propagation is equal to the product of the wavelength of the wave and the frequency of the wave. When I described the equation of the waveform of the wave. It looked like so. Y of x and t is equal to ym sine of kx minus omega t. So this was written for a wave that propagates in positive x direction, like so. What if the wave was propagating in negative x direction, in opposite direction? Well, if that were the case, then I would have to change the sign in the phase right here. And so this waveform is a waveform that describes a wave that propagates in negative x direction. So when you consider the waveform equation for a periodic wave, you must look at the sign in the phase to determine whether the wave is propagating in positive x direction or negative x direction. When the sign is negative, then the wave is propagating in positive x direction. And when the sign in the phase is positive, then the wave is propagating in negative x direction. So what factors determine or affect the wave speed of a wave in a medium? Well, first, the mass of the string per unit length is important. And this is known as linear density of the medium or string. Another term for linear density is linear mass density. Linear mass density, meaning the mass per unit length. And so the linear mass density is labeled with mu, and that is again the mass divided by the length of the string. This is similar to the volume density of some material, which would be the mass divided by the volume of that object made from that material. And so this is a constant for the string, no matter how much string we are dealing with. No matter what the length of the string is, the mass will be obviously changing, and so the ratio, though, will be constant. Okay. So then another factor that plays a role in the wave speed value is the tension in the string. And so when a string is more taut, then the wave will propagate faster in the string compared to when a string is less taut. So when there is some slack in the string, then the speed of propagation will be less. And I guess the analogy here to sort of visualize this is a guitar string. So if you take one guitar string and you tighten it a lot and pluck it, you will hear a certain pitch of the sound wave generated by the mechanical wave propagating in the guitar string. Now, if you loosen up the string a little bit and you pluck it again, you will discover that the pitch of the sound is different. And so this is related, as we will see later, to the speed of propagation of the wave in the string. And so tighter string, higher speed, looser string, slower speed. And so when we put both the tension in the string and the linear mass density, we end up with this expression for the speed of the wave. So the speed of the wave is equal to square root of the tension divided by the linear mass density. When a wave is generated in some medium, we already said that the medium itself does not move in the direction of the wave. So when a person creates a wave in a rope, the rope does not move away from the person. The particles in the rope only oscillate perpendicular to the direction of the propagation of the wave. So clearly, from that example, we know that material or matter is not transported by the wave. So what is transported then? Well, energy is what's transported by waves. And another analogy or example is electromagnetic waves. So electromagnetic waves can propagate in vacuum where there is no material to move around. So, but we know that the electromagnetic waves arriving from the sun are transferring energy, because when you are exposed to sun, you feel the warmth of it. And so this is a good example to show that material or matter is not transported by waves, but energy is. So then what is the expression for energy transmitted by a wave? Well, to answer this question, let's look at the wave that propagates along a rope in positive x direction. So the waveform is presented here in the graph. What we need to look at is how an element from the rope oscillates as the wave passes through that point of the rope. So let's look at a small element in the rope right here with mass dm. So we already know that this mass element here in the rope is going to oscillate up and down in a direction perpendicular to the direction of propagation of the wave. So in order to assess the kinetic energy that the wave carries, we must calculate the kinetic energy of motion of this mass element, like so. So that means that this mass element must be moving with some velocity in a vertical direction. So up and down, of course. And this we are going to label with U, and that is known as the transverse velocity of the mass element. So the kinetic energy transported by the wave as it moves along the rope is related to the transverse velocity of this mass element from the rope. And of course, that is the same for all mass elements in the entire rope. Well, so if I combine those two, the mass of the mass element, dm, the mass of the small element of the rope, dm, and the transverse velocity, and apply that to the definition of kinetic energy, then I get that the kinetic energy for this mass element as it's moving vertically up and down like so is calculated as 1/2 the mass of the element dm times the transverse velocity to the second power. So 1/2 dm times u squared. And so this is the kinetic energy with which this mass element is moving as the wave passes through it. And so this applies for all mass elements. And so if you sum all of these together, you would get the kinetic energy transferred by the wave. How about the potential energy that might be carried through this rope by the wave? Well, so in order for the wave to pass through the various points of the rope, for example, right here, that means that the rope must be compressed a little bit, since we have a sharp peak. But then when the wave passes through this section of the rope, it will get stretched a little bit. And then when the wave passes through this section of the rope, it's going to get compressed a little bit. When the wave passes through this section of the rope's going to get stretched a little bit. And so when you sum all of these instances of slight compression and slight elongation of the rope, the average result will be that the rope never changed length, and so therefore the potential energy term in the total energy of the wave is a zero. So only the kinetic energy term plays a role. In the sense of waves, talking about kinetic energy is not useful since we want to consider energy transport. So since energy is transported, we need to look at the rate at which the energy is transported. And so the rate of transport is known as power, and since we are averaging here, due to the fact that the waves are described by sine functions, we are going to talk about average power of the transmission of energy. I will show the derivation of this result after the lecture in a separate slide. But for now, the result is that the average power is equal to 1/2 times the linear mass density of the rope along which the wave is propagating, times the wave speed, times the angular frequency to the second power, times the amplitude of the wave to the second power. Notice that the linear mass density and the wave speed depend on the physical properties of the medium in which the wave propagates, so mass per unit length and tension, while the angular frequency and the amplitude depend on the process that generates the wave, so the generator of disturbances in the medium. So far I discussed single wave traveling in a medium, but what happens when more than one waves travel in a medium and they happen to be in the same region of the medium at the same time? For example, there are two waves shown here in the cartoon. One travels to the right and the other one travels to the left. And so those two waves meet along the rope at some point. Well, it turns out that waves obey the principle of superposition, which means that if we have several effects that occur simultaneously, the net effect is just the sum of the individual effects, meaning overlapping waves algebraically add to produce a resultant wave or a net wave, and the overlapping waves do not in any way alter the travel of each other. And so the cartoon here shows that. So the two waves traveling in opposite directions start to overlap, and then when they are completely on top of each other, we have a net wave that has an amplitude which is equal to the sum of amplitudes of the two individual waves. So that is the net effect, which is equal to the sum of the individual effects. And then once the waves pass each other, they are not altered in any way, shape, or form. They remain with the same amplitudes, they still have the same phases, and so on and so forth. So the two waves meet along the rope, superimpose on each other, producing a net wave. And then after that, they keep on moving, they pass each other, and they are not changed in the process. And so, if I wanted to write an expression for the net wave when the two waves interact with each other, then that expression will be simply the waveform of the first wave plus the waveform of the second wave gives us the waveform of the net wave. So adding the two waveform equations together results in a waveform equation for the net wave that looks like so. I will show a derivation of this waveform on a separate slide after the lecture. So the important part here is that we end up with two terms after some algebra. The first term is the magnitude term or the amplitude term. And as you can see, that depends on the phase difference between the two waves and on the amplitude of the waves. So here the important condition is that both waves have the same amplitude. They're not of different amplitude. So if the amplitudes were different, then this expression will be a little bit more complicated, but it's not really important for our consideration. So we are always going to consider waves with the same amplitude. Okay, and then the second term right here is the oscillating term. And so as you can see, to the standard phase that we are familiar with, kx minus omega t, a phase angle term is added. And so this is because the two waves are not in phase as they propagate along the rope. They are out of phase by an angle of phi. What this expression here allows us to do is, if we have the initial conditions where this sign here is equal to plus or minus 1, then we can calculate what's the amplitude of the resultant wave when the two waves meet on the rope. And so the process of creating of this net wave is known as interference of waves. So this example here is an example of two waves meeting each other at the same place at the same time in the medium, but this can be applied for more than two waves. And so the resultant wave will be just the net effect of all of them together. In real life, where do we see that? Well, many examples. For example, when you have more than one sound source around you, you can hear the sound from both or more sources at the same time. And this is a result of the interference of all these sound waves at your eardrums. Another example would be the observation of various objects around you. So what we see is the reflected light from a natural source such as the sun, and this light enters our eyes. So if we were not seeing multiple reflections from multiple objects, then we would only be seeing, let's say, one or two. And so, but we see multiple objects around us at the same time. So this is an example of multiple waves interfering together in our eyes so we can see them. Since the two waves that are going to interfere on the rope have different phases, the phase angle here actually is very important because the phase angle will determine whether this sine function here will have a value of 1 or a 0 or whether it's going to be somewhere in between. So we have two extreme cases depending on the phase angle, and those two extreme cases are known as constructive and destructive interference. So constructive interference is the superposition of the two waves when they're both in phase, which results in the largest possible amplitude of the resulting wave. And destructive interference is the superposition of the two waves when they are completely out of phase. And then the sine function in the net wave has a value of 0, and so therefore the net wave has no amplitude. So in the plots here on the right-hand side, we have two waves, one in blue and the other one in red, that interfere with each other, and the two waves are completely in phase. The two waveforms overlap. And so the result is a net wave that has double the amplitude of the individual waves that interfere with each other. In the second plot, we have two waves that have the same amplitude, one in blue and one in red, but are completely out of phase. So when one of the waves has a maximum, the other one has a minimum. And so when you combine the two waves, when they superimpose on the rope, they interfere to produce a net wave that has no amplitude. So this is an example of destructive interference, and this is an example of constructive interference. Let's label those. Constructive interference and destructive interference. And finally, the third plot here shows a intermediate result, meaning one of the waves has a certain phase and the other one is shifted by phase a little bit, and the phase angle is 2/3 pi. And so when you combine the two waves, the resultant wave has an amplitude that's determined by this phase angle as per this equation of the waveform right here. And so this is not the maximum possible amplitude, but it's not zero either. So it's somewhere in between those two cases. I should have mentioned that for constructive interference, the phase difference is phi equal to 0. So I said that the two waves are in phase. When the two waves are completely out of phase, then the phase angle is pi radians. So when two identical sinusoidal waves, identical meaning have the same amplitude, are in phase with each other, move at the same speed, and so on and so forth along the rope, when those two identical waves meet along the rope, the picture that is produced is called a standing wave. So the wave pattern on the rope remains constant with time. And so here's an example of standing waves. So we have one wave that travels down the rope, and then the rope is attached at the right end here. The wave reflects, travels to the left, and so when the two waves meet along the rope, they interfere in a constructive interference in some places and destructive interference in other places. And then this type of pattern is formed, and this pattern does not change in time. So there is no movement of these regions along the rope. They are fixed in place. If the speed of the wave is changed, then the standing wave pattern will look like so. If the speed of the wave is changed more, then the standing wave pattern looks like so, and so on and so forth. So multiple standing wave patterns can be created on the same rope based on how the speed of the generated waves. It can also be changed by the frequency of the waves or by the wavelengths of the waves. So for a standing wave created on a rope with both ends fixed, the net wave or standing wave equation looks like so. So the first term, again, the sine term is the amplitude term, and the second term, the cosine term, is the oscillating term. So in order to discuss standing waves on strings, such as, for example, string instruments, I need to introduce some terminology. So let's consider a standing wave on a string that's fixed at both ends. So this is my string, and it's fixed at both ends. So when a wave is generated, let's see if I can draw it nicely. Let's say I get a standing wave that looks like this. Okay, so notice how we have points where there is no amplitude of the standing wave, no oscillations. There are 3 of those points. And then there are regions here where we have the maximum amplitude of oscillations. So these have names. And so the points where there is no oscillations, here, here, and here, are called nodes. So these are the nodes. And then the points where we have maximum oscillations, here and here, are called antinodes. So we have, in this particular picture of a standing wave, we have 1, 2, 3 nodes and 1, 2 antinodes. And so this is the first snapshot of a standing wave here. For the other one, we have 1, 2, 3, 4 nodes and 1, 2, 3 antinodes. And next we have 1, 2, 3, 4, 5 nodes and 1, 2, 3, 4 antinodes. So when we are creating waves, or standing waves rather, on a string that's fixed on both ends, we have a requirement for nodes at the two fixed ends. So then that means that not all frequencies created on the wave, not all waves created on the string will produce a standing wave pattern when the waves interfere with each other. Only certain frequencies will create these. Only waves with certain frequencies will create these standing wave patterns. And so those waves have frequencies which are known as resonant frequencies. So then the question is, what are these resonant frequencies? So I will explain on a separate slide what that is and how we get them. But for now, here's an example of 3 different waves with 3 different resonant frequencies that are generated on a string that's fixed at both ends. So this first example is the example of the first harmonic. Then we have the second harmonic, and then we have the third harmonic. And so the general expression for the resonant frequencies in the series of harmonics that can be generated on a string that's fixed at both ends is given by this relationship here. So the frequency is equal to n times v divided by 2l, where n changes from where n varies from 1, 2, 3, and so on and so forth. V is the speed of the wave in the string, and L is the length of the string itself. Again, I will explain how these are achieved in a slide after this presentation. I'd like to discuss in a little bit more detail transverse waves, how the particles in the medium move with respect to the direction of propagation of the wave, and also the equation that describes the wave shape. Let's consider a string or a rope that is fixed at one end on the right side here, and it's free to move at the other end. So if we have a source of disturbance, and that source produces disturbances in a periodic fashion with equal amplitudes and constant frequency, then that is going to generate pulses along the rope, and when those pulses are stringed together, they will produce a wave down the rope. The wave is a periodic wave, and the waveform will look like so as propagating down the rope. So the direction of propagation in this case will be to the right. Let's look now at the individual particles in the rope and how they move as the wave passes through those particles. So the particles I will label with, let's use this color for that. So I'm going to draw a few just to illustrate the point. So here are some particles in the rope. And we will want to look at how they move as the wave passes through those particles in the rope. Okay, so as the wave passes through the first set of particles here, along the first hill, they are moving upwards. And so each of those will have vertical velocity. And this velocity will be different for the various particles because as the wave closest to the top of the hill here, the particles are moving with smaller and smaller velocity, since at the peak of the hill there is no motion of the top particle. So these particles are slowing down as they are moving up until rest when the wave passes exactly through each of them. So the top particle here has no velocity. It's stationary. And then after that, the particles start to move down with increasing velocity. The particle that passes through the equilibrium position has the highest velocity, the largest velocity, and then the velocities start to slow down until the wave reaches this particle here at the very bottom of the valley. This point is not moving. And then the particles after that start to move up as the velocity increases, and so on and so forth. So what we notice here is that the particles in the rope are moving vertically up and down, perpendicular to the direction of motion of the wave. So these particles are oscillating vertically. And so that applies for all of them. And so then if I wanted to write down an equation that describes the shape of the wave or the waveform, I must account for two variables. One would be a time component, which will describe where along the oscillation is a certain particle as the wave passes through that part of the rope, as well as where along the length of the rope or string is that particle. So the x component in the equation for the waveform tells us where along the rope is the wave at that moment of time. And then the time component tells us where along the oscillation a particular particle of the rope is. And so the equation of the waveform was y, and that's a function of position and time, is equal to ym, which is the amplitude, times sine of kx minus omega t. So the x coordinate here gives us again the position along the rope, and the time coordinate gives us the timing of the oscillation of each individual particle as the wave passes through that particle. Now I want to talk about the rate of energy transmission by a wave that's propagating along in a medium. And so that rate of transmission is just the average power that's carried by the wave. So first I will start with the expression for the kinetic energy term that is associated with a mass element from the string with mass dm. So this kinetic energy term was dk is equal to 1/2 dm times u to the second power, where u was the transverse velocity of the mass element in the string. So u was the transverse velocity. So the question is, how do I calculate the transverse velocity? The waveform is described by the function y of xt is equal to ym sine of kx minus omega t. So if I take the time derivative of that function, I'm going to derive a expression for the transverse velocity, since the velocity is the time derivative of the position function. So executing a time derivative of y of x and t, I get d dt of y of x and t is equal to d dt of ym sine of kx minus omega t. So when I execute the derivative, the term in the phase, which is kx, is not a subject to the derivative, since it does not depend on the time. Only the term omega t is the subject to the derivative. So the result of the derivative is minus omega ym cosine of kx minus omega t. And so this is the transverse velocity of an element in the string as it's oscillating up and down. I also need to relate the mass of an element in the string, dm, to the linear mass density of the string. So the linear mass density, mu, is defined as the mass of the entire string divided by the length of the string. But this is a constant for the entire string, and it doesn't matter how long the string is, because for each different length of the same string, the mass will be different and the ratio should be the same. So therefore, for a mass element with mass dm, I can calculate the linear mass density as the ratio of dm and dx, where the x is the length of this mass element. And so then from here, dm is equal to mu times dx. Well, now I can replace both those results in the original formula that's in the upper left corner for the kinetic energy. dk is equal to 1/2 dm u squared. And let's see what we get. So dk is equal to 1/2 mu times dx times minus omega ym to the second power cosine squared of kx minus omega t. I'm interested in the average power that's transmitted through the rope or string. And so power is in general defined as energy divided by time. So basically it's the rate of transferring of energy through the medium. So in our case, the energy that's passing through a element of the medium is dk. And so this will be proportional to the average power that's being transmitted through the medium. Now the question is, what exactly is this relationship? First, I will take the time derivative dk dt, and that will give me, without going through the entire calculation, 1/2 mu v omega squared ym squared cosine squared of kx minus omega t. And here, mu again is the linear mass density, v is the wave speed, omega is the angular frequency of this periodic wave, ym is the amplitude of the wave, and the rest is just a periodic function. All right. So now I need to find the average rate of energy transport. So I'm looking for the average rate of energy transport. I'm going to use the expression that I got for the rate of energy transport, and the only term that needs to be averaged would be the cosine squared of kx minus omega t. So to calculate the average of a cosine function, we are going to take an integer number of wavelengths, and knowing that the average value of a square of a cosine function over an integer value is of wavelengths is over an integer number of wavelengths is equal to 1/2. And then for the average of a cosine square, I will get 1/4. I'm sorry, I'm going to get 1/2. So one more time, the average value of the cosine square is calculated over an integer number of wavelengths, and this average value is equal to 1/2. And so when I combine that with the rest of the expression, I get that the kdt average is equal to 1/4 mu v omega squared ym squared. Finally, averaging over both potential and kinetic energies that are transferred through the medium, the final expression for the average power becomes P average is equal to twice dk dt average, or P average is equal to 1/2 mu v omega squared ym squared. Now let's discuss the principle of superposition of waves and how waves interfere to form a net wave when they meet somewhere along the medium in which they propagate. So in the lecture, I said that if we have two waves with wave functions y1 of x and t, and another one with a wave function y2 of x and t, the two waveforms will add to produce a net wave which I'm going to call y prime of x and t. So I want to discuss how I calculate the waveform of y prime of x and t. So for the purposes of the derivation, I'm going to consider two waves which propagate in opposite directions. So, and both have the same amplitude. So this will be y1 of x and t going to the right, and then I'm going to have y2 of x and t going to the left, and both will have the same amplitude ym. Okay, so the two waves, actually I will change this situation a little bit. I'm going to take the waves to go in the same direction, but they will have a phase shift. So both waves y1 of x and t and y2 of x and t are both going to the right, but one of the waves will be shifted by a phase angle phi from the other. Okay, so the waveform equation for wave number 1, y1 of x and t, is equal to ym sine of kx minus omega t, and y2 of x and t is equal to ym sine of kx minus omega t plus phi. So the two waves are shifted by a phase angle phi from each other. Okay, so adding the two together, y1 plus y2 is equal to ym sine of kx minus omega t plus ym sine of kx minus omega t plus phi. So there is a trig identity that can be used to add two sine functions. And so this is available in Appendix E in the textbook. I will write it here on the board so that it's clear what I'm using. So the identity states that sine of alpha plus sine of beta is equal to 2 times sine of 1/2 alpha plus beta times cosine of 1/2 alpha minus beta. So I'm going to use that and apply it to the above sum. So I'm going to assign kx minus omega t to be alpha in this identity, and kx minus omega t plus phi will be beta. Without going through the details of the calculation, the result is y prime of x and t is equal to 2 times ym cosine of 1/2 phi times sine of kx minus omega t plus phi over 2. The first term in the result here, 2 times ym cosine of phi over 2, is the amplitude of the resultant wave. So I can rename that as ym prime. And of course, since I'm talking about amplitude, I must take the absolute value of this expression, since it can be positive or negative depending on the argument of the cosine function. So this is absolute value of twice ym cosine of phi divided by 2. So when the two waves are, let's see, when phi is equal to 0, the cosine has a value of 1, so we then get maximum amplitude of twice ym. When phi is equal to 2 pi, then cosine is equal to -1, and so then the amplitude again has a maximum of 2 times ym. So for those two values of the phase angle phi, we get a resultant wave with maximum amplitude. And for any other values of phi, we get amplitudes that are smaller than the maximum, and of course the amplitude of 0 is included in that. For example, when the phase angle phi is, the phase angle here phi is equal to pi, then phi over 2 is pi over 2, and so then this cosine is equal to 0. The resultant wave has no amplitude, so there is a total cancellation of the wave when the two waves meet. Now let's discuss the formation of standing waves and resonance on a string that is tight at both ends. First, let's quickly discuss how a standing wave is formed. So I have a string that's fixed at both ends. And let's send a wave that has a waveform that looks like so down the string. And so the arrows indicate the direction of propagation of the wave. So once the wave reaches the fixed end on the right here, it's going to reflect from that point, and it's going to go back, and it's going to interfere with the incoming wave. And so the result of the interference is this standing wave pattern. So we have waves coming this way, coming back, coming this way, coming back. And so we discussed several important features of such pattern, and so those features were the nodes and antinodes. So the points where we have no amplitude of oscillation are known as the nodes, and in this case we have 3 nodes. And then the points where we have maximum amplitude of oscillations are the antinodes. So we have 2 antinodes in this particular standing wave. All right, so let's see if we can figure out some conditions that help us to determine the positions of the nodes and antinodes in a standing wave. So due to the nature of formation of standing waves, we have a wave that propagates to the right and then a wave that propagates to the left. So I'm going to investigate the superposition of those 2 waves and their interference, but this time I'm going to have the first wave y1 of x and t is equal to ym sine of kx minus omega t. So this one is going to the right, and then the one that's coming back to the left, y2 of x and t is equal to ym sine of kx plus omega t. So when the sign in the face becomes plus, that means that the wave is propagating to the left. When the sign is a minus, it means that the wave is propagating to the right. And so I will add the 2 waves and use the same trig identity that I explained in the previous slide. And so y prime of x and t is equal to y1 of x and t plus y2 of x and t. And combining the 2, I get that y prime of x and t is equal to twice ym sine of kx times cosine of omega t. So notice that this result here is not of the same form as the waves that I've combined to get that standing wave. So this is not a traveling wave. This does not move along the string. And of course, that's why it's called a standing wave. So this pattern here is constant with time. It doesn't change. So you can think of this term here in the bracket as the amplitude of oscillation. So that means that for nodes, this amplitude will be 0, and for antinodes, it's going to be maximum, so twice ym. So therefore, I can find a condition that is satisfied for the sine function so that the amplitude is either 0 or maximum. So let's look at the situations where the amplitude is 0 and when it's maximum. So the amplitude is 0 when sine of kx is equal to 0. So that means that kx is equal to n times pi, and n is equal to 0, 1, 2, 3, and so on and so forth. The reason for that is that sine is a periodic function. On the other hand, k is related to the wavelength lambda of the wave, as k is equal to 2 pi divided by lambda. So when I combine the 2 results here, I get my final expression for the position of the antinodes on the standing wave. So the position x is equal to n times lambda over 2. So the nodes are displaced by half of a wavelength, or distance by half of a wavelength. So this is for the antinodes. So similar calculation can be done for the position of the antinodes. I'm sorry, so there's made a typo here, so let's fix that. This condition here is for the nodes, not the antinodes. So now I will do the calculation for the antinodes. So for the antinodes, we want the condition that the sine function satisfies to be that the sine function is equal to 1. It has a maximum. So we want sine of kx to be equal to 1. And I'm going to use an absolute value here, since the sine function can be also -1, but that will always correspond to -1 or +1 will always correspond to the amplitude of the wave. And so when is this condition satisfied? Well, this is satisfied when kx is equal to pi over 2, 3 pi over 2, 5 pi over 2, and so on and so forth. And so I can rewrite this as kx is equal to n plus 1/2 times pi, and n is again equal to 0, 1, 2, so on and so forth. Again, combining with the relationship between k and the wavelength of the wave, k is equal to 2 pi divided by lambda, I get my final expression for the positions of the antinodes along the standing wave. So the antinodes are positioned at those distances calculated as n plus 1/2 lambda over 2, where n is equal to 0, 1, 2, 3, and so on and so forth. So antinodes. So if you have a standing wave and you need to calculate the positions of the antinodes, then you would use this relationship. And if you have a standing wave and you need to calculate the position of the nodes, you would use this relationship. Finally, let's talk about the harmonics that can be generated on a string with both ends fixed. So when we have a string that's fixed at both ends, not all wavelengths or all frequencies of waves can be generated on that string. Only certain ones can be generated, which will produce standing waves. All the other waves will die out with time. So the waves that can be sustained on a string and produce standing waves form the harmonic series. And so there is a relationship between the frequencies of those waves and also between the wavelengths of those waves. So I will write down the general relationships that determine the frequencies and the wavelength, but I would like to show you how the derivation of those general expressions happens by considering the first, second, and third harmonics that can be generated on a string that's fixed on both ends. So here is my string that's fixed on both ends. So both ends have nodes, and the length of the string is L. So my derivations will relate the wavelengths of the waves generated on this string with the physical length of the string. And then after that, I will be able to derive an expression for the frequencies as well. So the first harmonic would be the wave that has the longest wavelength that can create a standing wave on this string. So the wave will look like so. So the wave is propagating to the right. It reflects from the right fixed end of the string, and then it goes back to the left. And so this is a standing wave pattern. So now, how many wavelengths fit the length of the string? Just a half of a wavelength. So the wavelength from here to here, from the left fixed end to the right fixed end, that's just half of a wavelength. And then on the way back, we have another half of a wavelength. So the longest wavelength that can fit this string is just a single wavelength. 1/2 plus 1/2 is equal to 1 full wavelength. So then I can relate the wavelength of the wave to the length of the string simply by writing that lambda over 2 is equal to L, and from here the wavelength of the first harmonic is equal to 2L. And let's label this first harmonic. Okay, now let's see how the second harmonic wavelength is calculated. So here's my string again, fixed at both ends. The length is L. So now I already fitted the longest possible wavelength that will generate a standing wave on the string for the first harmonic. So now I need to fit the second longest wavelength possible. So that means that I will have another node in the middle here, and so the wave now looks like that. So that's the wave that propagates to the right, then it reflects from the fixed point, goes back to the left, like this. And so what do we have here? We have half of a wavelength plus half of a wavelength, and then on the way back we have half of a wavelength and then another half. So then the relationship between the wavelength of the wave and the length of the string is this is lambda over 2, this is lambda over 2, this is lambda over 2, and this is lambda over 2. So we have lambda over 2 times 2 is equal to L, or in other words, lambda 2 is equal to L. So this is the second harmonic. And similarly, I can do the third harmonic. So here's my string again, fixed on both ends. Now I'm going to have two nodes here on the string, and the wave will look like this. So that is the wave that is going down the string, and now after reflection we have, oops, there's a different color. We have the wave going back, and so this is a standing wave pattern. And so each branch here is lambda over 2. And so we have 3 times lambda over 2 fitted in the length of the string L. So 3 times lambda over 2 is equal to L, or lambda 3 is equal to 2L divided by 3. And so this is the third harmonic. And so similarly, the wavelength for the other harmonics can be derived, but now I have enough information to derive a general rule for calculation of the wavelength of all harmonics. Before I do that, let's also look at the frequencies. So to calculate the frequencies, I'm going to use the relationship between the speed of the wave in the string, the wavelength, and the frequency. And so I'm going to put this in the upper left corner. So we know that the speed is equal to the product of wavelength and frequency. So from here I can solve for the frequency. And so for the frequency of the first harmonic, I get that F1 is going to be equal to V divided by lambda 1, which is 2 times L, so V divided by 2L. For the second harmonic frequency F2, I get that this is equal to V divided by L, but I'm going to write it as 2 times V divided by 2 times L. And the reason for that is that I will then generalize the rule for the frequencies based on these values. For the frequency of the third harmonic F3, I'm going to write this as 3 times V divided by 2L. Alright, so now I'm ready to write an actual rule for the wavelength and for the frequencies of all possible harmonics that can be generated on that string with length L. So for the wavelengths, I get that lambda n is equal to 2 times L, so twice the length of the string divided by n, where n is 1, 2, 3, 4, and so on and so forth. And n corresponds to the harmonic, so n1 is the first harmonic, n2 is the second harmonic, n3 is the third harmonic, and so on and so forth. For the frequencies of the harmonics, I get that Fn is equal to Nv divided by 2 times L. So V is the speed of the wave in the string, L is the length of the string, and N is 1, 2, 3, so on and so forth. So for Fn, the first harmonic, N is equal to 1. For the second harmonic, N is equal to 2. For the third harmonic, N is equal to 3, and so on and so forth. And so based on that general rule for the frequencies of the harmonics, I also can write a rule that relates the various frequencies themselves. And that rule is that the nth harmonic frequency is equal to n times the frequency of the first harmonic. And of course, n here is, again, 1, 2, 3, and so on and so forth. And so this concludes all the derivations and explanations that I wanted to present to you after the slides of the lecture, to clarify how some of the results are achieved in the chapter. So we are going to use some of these when we do worksheet problems.